Let us take up another problem which is connected to rolling motion again, but two springs are connected. Let us say it is a disc which is placed on a rough horizontal surface. It is not a smooth, it is a rough horizontal surface. There is enough friction so that at the point of contact, in case of rolling, the velocity is 0. One spring of constant K connected the top edge of the disc. The other end is fixed. Okay. Another spring connected to center of the disc, other end is fixed. Look at this. Okay. There are two springs connected at two different places, and the total system is placed on rough horizontal surface. Let R is the radius. Okay. Now, if I give a small displacement, a small angular displacement, leave it, then it executes simple harmonic motion. Let us find out the frequency of this oscillation. So again I am using my energy method. What is the energy method? Write the total energy of the system. The total energy remains constant with respect to time. Differentiate. From that, A is equal to some constant into X, will get it. So here of, right now, let X is the compression of this spring. Okay. The same X is the displacement of this center of mass. Okay. And if X is the compression of the spring, what is the extension of the spring? That is a key point here, you have to observe that. Okay. We know that if V is the velocity of center of mass in case of rolling, the velocity of the top edge is 2v. If V is the velocity of center of mass, the velocity of the top edge is 2v. Then the extension of this is 2x. So that's what we have to do. Very, very important thing is, if it compresses by x, the spring will be extended by 2x. Let us write the total energy of k x square for this spring plus of k 2x whole square, the total energy stored in this spring, plus of m, where m is mass of this disc, into v square, where v is velocity of the center of mass, into, since it is a rolling, of k square by r square, k dash, better write, k dash. What is k dash? The radius of gyration is equal to constant. If it is a disc, this k dash square by r square is nothing but half, is substitute. You differentiate both sides with respect to time. From that, you prove that A is equal to again minus omega square x, and find out omega value. That is the angular frequency of SHM. From that, you can find out the time period. Okay. And here, one of the key point you have to observe is, if x is the extension of the spring, 2x is the extension of the other spring. Okay. So calculate the total energy of this plus rolling energy. Okay. Half mv square and 1 plus k square by r square. Okay. So this is the strategy we have to adopt when the system is little bit complicated. So if we can solve by force method, but if we apply energy method, it is very easy to calculate by using a differentiation technique. Next, let us take the SHM connected to fluid mechanics, because SHM is the one chapter where you can find application different branches. Fluid mechanics. Here a spring of constant K, connected to a small object, or you can take it a cylinder of mass m. A spring of constant K connected to a cylinder of mass m. If you pull down, then it executes SHM, which already we solved in earlier classes. Now, this cylinder is completely immersed or partially immersed. Let us say it is a partially immersed. It is partially immersed. Okay, that's all. So now, if I pull down by x, and leave it, then it executes simple harmonic motion. You have to find what is the frequency of simple harmonic motion. Only the extra is, in addition to the restoring force due to spring, there is one more force acting up, that is upthrust. We know that the formula for upthrust is VL dl g. According to principle of buoyancy, whenever an object is immersed partially or fully, it experiences an upthrust. That upthrust is equal to the weight of the liquid displaced. Here, what is VL? The volume of the liquid displaced by this object. dl is the density of liquid, and g is the acceleration due to gravity. Now, the total restoring force which is acting up is spring force Kx plus VL dl g. That is the total restoring force acting up. Now, F is equal to minus Kx. Then what is this VL? Volume of the liquid displaced by the object. Let us say if it is of cylindrical shape, the extra upthrust it explains is area of cross section into x. Okay. The extra upthrust, because of whenever it compressed by x, the extra upthrust is volume is area of cross section of the cylinder into x into dl g. So, F is equal to ma, which is equal to minus of, take out k x common, x. So, we can again prove that A is equal to minus omega square x. The constant of proportionality between acceleration and displacement is omega square, which is nothing but k plus A dl g by m. From that you can find out omega, the angular frequency of SHM. So, only thing extra is, that means a knowledge of principle of buoyancy is required to solve this problem. Let us take up another example where the object is completely immersed. the object is completely immersed in a non-viscous liquid. Even earlier case also the liquid is non-viscous, that is no friction between the object and fluid. So, let us say that a rod is fixed here, its edge. D2 is density of liquid, D1 is the density of solid. It's fixed here. Now, give a small angular displacement. Give a small angular displacement. Theta. And leave it. Then it executes simple harmonic motion. Then how do you calculate its frequency of oscillation? Look at now. The gravitational force mg is acting down. At same point, upthrust is acting up. Okay. The resultant of this mg and upthrust produces restoring torque, which is nothing but torque tau is equal to mg minus upthrust. What is upthrust? V d2 g. What is V? Volume of the liquid displaced by this object. When object is completely immersed, is nothing but volume of the solid. We can write volume of the solid is mass of the solid divided by its density into arm. What is this perpendicular distance? Perpendicular distance is L by 2 into sin theta. Okay. This is the restoring torque produced by the gravitational force and upthrust. In case of small angle, tau is equal to minus of mg minus v d2 g L by 2 into, for small angle theta can be replaced by sin theta can be replaced by theta. Okay. Now, in place of tau, I can write again I alpha. Okay. We know that tau is equal to I alpha. I alpha is equal to some constant into theta. From this, we can again prove that angular acceleration alpha is equal to minus of omega square into theta. Angular acceleration is directly proportional to angular displacement. From this proportional constant equate to omega square, we can find out with what frequency it oscillates. So, that is a one more SHM which is connected to fluid mechanics. So, today we discussed the SHM related to rotatory motion, rolling motion and fluid dynamics. Okay. So, similarly, the SHM is not only connected to this, it is also connected to thermodynamics. Even electricity also we can relate it, even electromagnetism also. In the later classes, we are going to discuss some more problems connected to SHM and the other topics of physics. Thank you.